Hi, I'm Joe Paiva, and this is just a little explanation of what weighted bearings are and how you might compute them. So one of the first questions that happens is, I've never had to weight bearings before. Well, it's most often applied when we're working with the US Public Land Survey System, and it's used to compute the midlines of fractional sections when there are no opposite quarter corners to connect to get that midline, regardless of which direction we're going. There are probably other non-USPLS situations where they can be creatively used to create some kind of an optimum bearing. So I'm taking, so on GeoLearn, one of our faculty is Dennis Muland, and he actually has a series of lectures that you can get for continuing education if you are a licensed professional on the topic of fractional sections, and in there he talks about a weighted mean bearing. But Dennis recently came out with a book called Public Lands Retracement in the 21st Century, and on the pages I have shown here and a couple of figures, he has an example. Now, I'll tell you that my figure does not really fit with what Dennis has drawn. I just did it for a little bit of efficiency in viewing on video. But basically we have a section that's fractional. There's a river or something going through it. It could be anything. And so we have some government corners that were set and some lines that were run to, in this case, to the river. So because there's no opposite quarter corners, actually there's no opposite quarter corners both in the north and the west. But in this case, we're interested in what is the direction of that midline, what I showed there as a dashed line. What should that be? So the GLO notes show, or BLM notes, depending on when this was done, show north 8825 west, 1250 feet, south 8845 west, 2105.35 feet, and south 8930 west, that's just one west, that's a typo on my part, 2632.5 feet. So what do you do? So what I say is basically you do a vector sum of the three lines, and you might go, what? I've got to go back and learn vector algebra? No, what it means is what you always have done, but you might be not used to doing it by hand, but what you do in a traverse computation, you compute the latitudes and departures of the lines, and then you sum them and then do an inverse to get the direction of the line, which would be the weighted mean bearing. So when it comes to latitudes and departures, just as a reminder, if we have a line that goes off in this direction, and if this is north, hopefully you all know this, but we basically have a departure and we have a latitude. So the departure is the east-west component of the line, and the latitude over here is the north-south component of the line. Now the bearing angle is actually this angle here, so even though I've drawn the triangle here, south and east of the line, hopefully you all realize, let me just change colors, that the latitude is actually this part, and the departure is actually that part. So when you look at this, you have a right triangle, you have this angle here, so hopefully you can figure out that by using the sine and cosine of this angle, I'm going to call it beta for the bearing angle, and multiplying it by the length of the line, you can get the latitude and the departure, and we'll go through this here in a second. So here are I've just tabulated the latitudes and departures, and so if we take 8825, of course we have to remember to first convert it to decimal minutes, and then you take the sine and cosine, or if you use the polar to rectangular conversion, if you have such a function on your calculator, you get latitude and departure of, I pre-computed this just to save some time, 3454 and minus 1249.52. So keep in mind that if it goes west or south, you apply a negative sign in front of the departure latitude as it may apply. And if you're going north and east, you have a positive, and obviously don't have to put the positive sign down. But sometimes people do it. Why? Because especially in a test situation, you could be very stressful. You're doing the math fast, and you should come back and apply the signs later if you're using bearings. Now, another way to get around this is to actually use azimuths, convert all the bearings to azimuths, because if you put in the azimuth, you'll automatically get the correct algebraic sign for the latitude of the departure. But anyway, this is going north and west, which is why it's positive and negative as far as the signs are concerned for latitude and departure. Then for the next line, we have a negative 2297 and a negative 2632.40. And then for the last line, we have a negative 45.93 and a negative 21.04.85. So when it comes to these computations, I just wanted to point out something to you. Let me bring up this calculator. And so keep in mind that you have functions on calculators that will do things like convert degrees, minutes, and seconds to decimals. So make sure that you don't forget to do that kind of thing. So just as an example, if you put in 8825, which is the first line, and you punch it in as a decimal like that, you can't take the sine or cosine of that. You have to first convert it to decimals. So what people usually will do is take 25 divided by 60, get a fractional number, and then add the 88 to it. But you do have a function on your calculator. On this particular calculator, it happens to be right here. It says arrow H. So I'm going to hit arrow H, and it converted it to 88.4167. And as someone, even in the exam, you should always be double checking your work. And you know that 8825 is a little bit less than 88.5. You might know that 8824 is a multiple of tenths of a minute. And so you might kind of figure out that it needs to be more than 88.4, and you know it needs to be less than 88.5. And so that's kind of a little bit of a check. The other thing I just wanted to point out is people always get confused. So let me just move this here and talk about the first line. This is a line that's basically going very close to due west. And they always get confused. Well, do I use the sine or the cosine to get latitude and departure? Well, here's one way to find out. This line is going very close to due west, so the departure should be very close to the to the length of the line. So the departure or the function should be very close to 1. So I'm just going to do a trial and hit sine. Oops, there. And the sine came out to be 0.9996. So it's telling me that when we compute departures, we use the sine function, and obviously the other one would be the cosine function to compute latitudes. So that's just a little computing trick that I just wanted to point out, because I find this with college students as well, that they don't do this enough. Check that they're actually keying in the numbers correctly and then using the correct functions. And some of it could be just mistyping because you're working fast, especially in an exam situation. So in this particular case, we get minus 34.36 and minus 5986.77. And this is why the signs are important, because obviously we have one positive, a northerly direction for one latitude, two southerly latitudes, but all three of the departures are westerly, so all three of them are negative. So that's really important. Once you do that, you basically do the inversing. And so the inversing is always done this way for the bearing angle. Now, remember, we don't care about the length of the inversed line because we're just trying to compute the mean weighted bearing. So what we do is we take the departure, which is in this case minus 34.36. We divide by minus 5986.77. It turns out because the numerator and the denominator are both negative, it doesn't really matter whether you carry the sign, because when you divide a negative number by another negative number, you get a positive result anyway. So you're going to get a first quadrant angle. And so what you do is, when you compute this, and let me pull up the calculator again. So let me clear that number in the display. So we have 34.36, and I need to change the sign. I want it to be negative if you have forgotten or you're in the throes of the exam and you're just typing stuff in. Like I said, if you had time to think about it, you would know you didn't really have to type in the negative sign because you're not going to type it in for the numerator either. So I've typed in the 34.36, so then I put in the 5986.77, and since I put in the negative side for the numerator, I got to do it for the denominator, so there's the negative. Then I hit my division function. I hope you guys are all okay with RPN calculators. It's my favorite. And then what we're going to do is take the arc tangent. So the arc tangent would be this function right here, and I get 3288 degrees. Now keep in mind that's not degrees, minutes, and seconds. On the exam, it's probably degrees, minutes, and seconds. Well, you know it's 0 degrees. Can you tell that it's more than 18 minutes, but less than 24, because it's 0.3 something. 4/10 of a degree would be 24 minutes. So on this particular calculator, we do have a function to convert decimal degrees back to degrees, minutes, and seconds. On this particular calculator, it's abbreviated h.ms, but as you probably know, hours, minutes, and seconds, and degrees, minutes, and seconds both use base 60 arithmetic. So I'm going to hit that function, and I get 1944. Now, keep in mind that you still have to assign a bearing to this. Because it's going southerly and westerly, right, it's going to be south 19 minutes, 44 seconds west. So that's the solution to this particular problem. Let me get rid of the calculator. And move on to another example. This one was sent to me by someone who was taking the state-specific exam in a particular state, and they had a sample test. And this particular person, a professional land surveyor, was actually registered in 12 or 15 states, had never run into this before. He sent it to me and said, how do I solve this? So you can see again, it's a fractional section, and the distances are in chains, and this time we have degrees, minutes, and seconds, although we have one easy line. This line B is north 0000 west, meaning due north. So just to walk through this one, I put it in a table, and I'm not going to handwrite things just to make it go a little bit faster. But when I used chains for the distance, rather than convert them to feet, what I did was I carried The decimal places a lot more because if we only carried it to 2 or even 3 or 4 decimal places, it might not be enough because we want to get some resolution to be able to get down to the nearest second. So in this particular case, I carried it out to 5 decimal places, and there's actually an analytical system I can go through in another lecture if you'd like on how you do that. And one of the first things you do is you compute your latitudes and departures, then you come back and check your signs. So this is north, this is north, this is north, so we should have a plus here and a plus here if you want to confirm that you did that correctly. And then you have west, west, and west, and you see here we have west, west, and this second line in the table runs due north, so you could, if you want, have a sign or not have a sign, it doesn't really matter. So then when you sum them, you get a negative departure and a positive latitude. So this line is going north and west. And I say this line because this is the midpoint for that line. So you calculate, so here again, I've drawn the particular triangle. Obviously the 0.46 is totally out of scale with the 112 because these are all in chains, but I drew the sides of the triangle over here, but the actual angle we're solving is this one here. But you can just as well solve this opposite angle. It's the same angle, and so it's 0.46084 over 112.05893, you take the arctangent of that, you do get a negative number, which can sometimes help you remember, okay, I'm in one of the quadrants where the tangent is negative, if you know what that means. And then, of course, you have to remember that you get the answer in decimal degrees, which means you need to convert it to degrees, minutes, and seconds. But then you come back and say, okay, I'm going north because this is positive, I'm going west because this is negative, and there's your answer. I hope this was helpful.